Okay, so to begin with, we will start with, this one is not the question from last time, but this one is similar one. So we could start with this question. Let's get rid of the, simply because we already know that the separation somehow is going to depend on the spacing of the slits. The spacing of like if you have a two-slit situation, and you have light here, and then meet at some point here, we already know that there's going to be this form here, and we know that there's a path difference, and this is going to be, if this distance here is d, then this is d sine theta, and that must be equals to m lambda. And we know this distance, if this distance is big D, and this distance here is y, so is y from the, if this distance from the center is y, then C, he says, how does the spacing, so if this spacing that they're referring to. So let's repose this question and see what happens. Remember, you can speak to your neighbor. Okay, so let's see a pattern. You see that? Right? As this light. So the idea, the light then it basically spread out as this slit gets narrower and narrower. And that has a lot of practical use, as we see in with, like, for instance, in your lasers and so forth, that happen. Okay, so what we notice, this is what we really see when light goes through a very small slit. So we don't see this, but we see this separation. And basically, we basically would see these higher order maximas, which is shown here in this figure. So it says here is the pattern you will see. Notice that in figure 2 that there are several bright spots and dark areas. So you see this is a dark area here. This is your central maximum right here. And the dark spot as you do what? Okay. Why the dark spot occur, John? Because of destructive interference, and the bright spot is a result of constructive interference. So we say we can, we said that when theta is small, this is approximately equals to theta, right? So then what that means that since we also know tan theta is equals to y over d, and we know that d is equals to m lambda, and for when theta is small, this is also equals to theta. So therefore, we know from this equation here, that theta is equals to lambda over d. So therefore, we can see this is m lambda over d, and y equals to this, and we want to find the behavior of y which gives you this equation and tells you that as I change the, as this gets smaller, y gets bigger, right? So as this gets smaller, y gets larger, this distance gets larger, and as this gets larger, y gets narrower. right? So this is the equation you basically want to use for because now if you increase the number of slip, then that means we're going to say ND then must be equal to sine theta, which is equal to M lambda. So increasing the number of slip is going to only make your wave profile more narrow, but yet sharper, right? So they will be brighter when you have a lot more slits. Okay, so here we have an example. In this example, again, in this this example more or less fit this here, but again, we have this single slit here. We know the width of the slit is A. We know the distance the screen is from the slit, and in this case, he asks what is the wavelength of light. Well, we know the spacing of the fringes, and because we know the spacing of the fringes, we can use this analysis that I just did here, and then we can show that lambda is equal to the spacing of the fringes times the width of the slit over the distance from the slit. And that gives us this answer, that lambda equal to 600 nanometers. What's the wavelength of infrared light? Huh? You said?
It's at 1400, but that's microwave.
Yeah, 1400 is really large. What's the wavelength of, say, radio wave? Huh? No, that's actually the limit of visible light. Huh? 9380? That's actually infrared. 380, that's actually ultraviolet. Huh?
Radio wave?
Yeah.
1/1000.
No, it's probably about what? Maybe about 2,000 or
Because the
more.
frequency is 1,000, right?
Eh?
Radio frequency?
Radio frequencies of the problem? So you might be, yeah, you might be right, because infrared is just, yeah, you might be RF is between about 1,200 to about 1,800, so that makes sense. Yeah, RF frequency should be that, which is what these are. What do you think? Your flickers is based on RF frequencies, radio frequency. But yeah, the visible light is about, say, 450 to about 700, where blue light is about 450. So blue light is high energy and red light is low energy. The red light is about 700. Okay, you need to know that for your exam. Yeah? Yeah? I just gave it to you. So about 450 to about 700. Huh? Okay, let's accept 319. Maybe I'm giving, let's see, we ultraviolet, not ultraviolet, we purple light comes. Okay, that's why, the purple is below blue. Okay, that's why. Purple is a much higher energy. Image, so like for instance, when you're looking, in the night, your car is driving to you, it's far away, right? It's very hard to tell whether it's a car or a motorcycle, right? Because you're just seeing one light, right? But as it gets closer to you, then you're able to resolve. But there's a point just before, right, which will be your limit. And beyond that point, it will become really clear that you can say, definitely, this is a vehicle with four wheels. Unless it's not one of those guys driving their car with one light. I hate that. Okay, at this point, we reached the end of what we have to discuss today. So this is a summary of everything we have done. So I will put up these slides sometime today. So again, going back to this is a diffraction grating equation, which is very similar to the interference equation, right? So that's what we have to look at. Also, we see that when light goes through a slit, then you don't get one light, but you get a separation. So we get bright, a mixture of dark and bright fringes, and it's governed. The dark fringes are governed by this equation.
Straight, the dinosaurs all met their fate. They tried to leave, but they were late and they